Hello students, welcome to the digital classes. In today's class, we will learn conservation of momentum. In the earlier classes, we have studied motion, speed, velocity, acceleration, equations of motion and laws of motion. Let us have a look at topics once again. We have seen objects in motion, objects at rest, distance, displacement, speed, velocity, average speed, average velocity, equations of motion. The three equations of motion are v equal to u plus at, s equal to ut plus half at square, v square minus u square is equal to 2as, where u is the initial velocity, v is the final velocity, a is the constant acceleration, s is the displacement covered in the time t. In the earlier lesson of laws of motion, we have discussed that Aristotle in his treatise on the heavens argued that a constant force is necessary to keep the object in uniform motion, and that was a wrong idea which was believed to be true for many years. We have seen Galileo's experiments, and what Galileo has concluded from his experiments is that objects in motion would continue to be in uniform motion on level surface unless disturbed by an external agent. And then we have discussed Newton's laws written in Mathematical Principles of Natural Philosophy by Sir Isaac Newton. The first law says every object continues to remain in its state of rest or uniform motion until an external unbalanced force acts on it. In other words, we can say object at rest wants to be at rest and objects in motion want to be in motion. The first part, that is object at rest wants to be at rest, is called inertia of rest, and object in motion wants to be in motion in the same direction is called inertia of motion. Greater the mass, greater is the inertia, and we can define mass as the measure of inertia. Then we have discussed momentum, which is the product of mass and velocity of an object. Every object which is moving possesses momentum. Its SI unit is kg meter per second. And then we have discussed Newton's second law, which says the rate of change in momentum of an object is directly proportional to the external unbalanced force and is in the direction of the force. In other words, Newton's second law can be stated as the vector sum of forces acting on an object is equal to mass multiplied by the acceleration, F is equal to ma. And from Newton's second law we can understand that greater is the mass, lesser is the acceleration, and lesser is the mass, greater will be the acceleration for the same force applied. Here is a video which demonstrates that greater the mass, lesser is the acceleration. And finally, Newton's third law, which says every action has equal and opposite reaction. Here action and reaction mean forces. We have seen in the case of a balloon, where balloon pushes the air outside and the air pushes the balloon forward. We have seen this in case of a toy car. Similarly, rocket works on the principle of Newton's third law. Rocket pushes the exhaust gases outside, the gases push the rocket forward. In today's class, we will discuss free body diagrams, impulse, conservation of linear momentum and related numericals. Children, from Newton's third law, we have learned that every action has equal and opposite reaction. Children, let us see normal reaction in this example. Here we have an object on a table, its weight, that is the gravitational force, acts downwards. The surface will exert equal and opposite force on the object, that is upwards. This force is called normal reaction. Children, let us learn how to draw a free body diagram. A free body diagram is a diagram which shows all the forces acting on the object. Here is an example which is taken from the textbook. On this object, there are several forces acting on the object. Let us consider the forces acting on the object separately. the external force F, which is given by blue arrow, is acting on the object. This is the external force. Its weight is acting downwards, which is given by the purple arrow. This is the weight acting downwards, the weight is gravitational force. Then we have normal reaction acting on the object from the surface upwards. This normal reaction can be drawn anywhere on the object, but the direction should be upwards. Next, there is frictional force. Because we have applied external force, the object tends to move towards right, and then there is friction between the object and the surface, which acts exactly in the direction opposite to its motion. So, when we draw all these forces acting on the object, we call this as a free body diagram. Children, I would like to introduce something called as internal force. We all may sit in a bus or auto or any vehicle and push the vehicle forward. Do you think the vehicle moves? No. Why? It is because when we are inside the bus and we apply a force, that force is internal force, and every internal force has equal and opposite force from Newton's third law, and hence the bus does not move. Children, let us consider another example where there are more than one force acting on the object. Here is mass m, there are two external forces, one is F1, another one is F2, both are acting in the opposite directions. Apart from these two external forces, the two more forces which are acting on the object are, one is weight and the other one is normal reaction. Because normal reaction and weight are equal and opposite, we can ignore them. Now, we have two forces acting on the object in the opposite direction. If F2 is greater than F1, then the object moves in the direction of F2. The net unbalanced force is given by F2 minus F1. In case F1 is greater than F2, then the object tends to move in the direction of F1. The net unbalanced force is given by F1 minus F2. The external unbalanced force is F. So, whenever there is an external unbalanced force on an object, that produces an acceleration. So, F is equal to ma. This is from Newton's second law. The acceleration on the object is found from the equation F is equal to ma. So, acceleration is equal to F by m. Now, let us solve some numericals on this equation F equal to ma. Here is an object whose mass is 5 kg and a force 20 Newton is acting on it. The weight and normal reaction are balanced and hence we need not consider them. Friction is not mentioned in the question, so we need not consider that too. So, to find out the acceleration, use the formula A is equal to F by m. Substituting the values, acceleration is equal to 20 by 5, which is 4 meter per second square. Here is another question. A force of 20 Newton acts on the same object of mass 5 kg. Friction between the ground and object is 5 Newton. Find the acceleration. So, here an extra quantity, that is frictional force, is given. So, what we have to do is, to find out the acceleration, we should find out the net force, that is external force 20 Newton minus frictional force 5 Newton, which is 15 Newton. So, acceleration is equal to force by mass, which is equal to 15 by 5, 3 meter per second square. Children, let us make this question a little more complicated by asking a few more quantities. So, in the same question, we should find out the velocity after 8 seconds. Now, we know that net force, which is unbalanced force, that is 15 Newton. From that we can find out the acceleration, that is 3 meter per second square. Let us find out the final velocity. The object was at rest in the beginning when the force was applied. So, initial velocity u equal to 0 and acceleration produced by the force is 3 meter per second square. Using the equation of motion v equal to u plus a t, v is equal to 0 plus 3 times 8, substituting the values, we get v equal to 24 meter per second. Children, let us find out the distance covered by the object in these 8 seconds. We found acceleration which is 3 meter per second square. We found velocity to be 24 meter per second at the end of 8 seconds. To find out the distance, we use the formula s is equal to ut plus half at square. U, which is initial velocity, which is 0. So, distance is equal to 0 into 8 plus 3 times 8 square divided by 2, which comes out to be 96 meter. Children, let us consider when a force is acting on more than one object. Here we have two objects whose masses are 3 kg and 2 kg. These two are connected by a rope, and when a force of 10 Newton is applied on 3 kg towards left, so there will be a tension which is developed in the rope, and due to that tension there will be a force on the mass 2 kg. In the rope, a tension T is created. The force 10 Newton acts on 3 kg and 2 kg. Here the force is acting on the total of 5 kg. The total mass of the system is 3 kg plus 2 kg, which is 5 kg. The acceleration produced is force by m, which is 10 by 5, which is equal to 2 meter per second square. The tension in the rope produces an acceleration of 2 meter per second square. So, the tension must be equal to mass multiplied by acceleration, that is F equal to ma. Using that formula, we get mass which is 2 and acceleration which is also 2. So, 2 times 2 gives you 4 Newton. So, the tension in the rope is 4 Newton. Now, let us consider what happens when force acts on a moving object. When force acts on moving objects, in case the direction of force is same as the direction of its velocity, then the velocity increases. The object continues to move in the same direction with its velocity increasing. In case force acts in the direction opposite to that of velocity, in this case the velocity decreases. The object continues to move in the same direction till it stops. If the force continues to act, then the object starts moving in the opposite direction. Children, we have observed that whenever force acts on an object, its momentum changes. The change in momentum is called impulse. Impulse is the change in momentum which will be equal to force multiplied by the duration for which the force was applied. Impulse is equal to change in momentum, which is force into time. In any situation where the impulse is constant, the force of impact will be inversely proportional to the time taken. Consider an object which is moving with some velocity. So, let us consider an object which is moving with velocity v, mass of the object m. Here the initial momentum is given by mass multiplied by velocity, that is mv. When a force is applied to stop it, then the velocity becomes 0. Let the force be applied for a time t. The impulse is change in momentum. The final momentum is 0. So, change in momentum is 0 minus mv, which is equal to minus mv. The negative sign here indicates that the momentum is decreasing. So, whenever the force is opposite in direction, the momentum decreases. So, the impulse is minus mv, which will be equal to force into time. Children, let us say the mass is 5 kg and the velocity was 20 meters per second. Let us see in different cases how the time and force will be. So, here the mass of the object is 5 kg and velocity is 20 meters per second. The change in momentum will be equal to mv, which is 100 kg meter per second. This should be equal to force into time. Let us say we apply different forces and let us see what the time will be. To stop this object by applying 10 Newton force, the time that would be required will be 10 seconds. To stop the same object in 2 seconds, we have to apply 15 Newton force. If we apply a force of 100 Newton, then the time required would be 1 second. In case if we apply 500 Newton, then the object would stop in just 0.2 seconds. In case if we apply 1000 newtons, the time taken would be 0.1 second. Children, we have seen that to stop an object, we have to apply a greater force to stop quickly. That means, if an object which is moving, if it has to stop, a greater force has to be applied in order to stop it quickly. Let us do an activity to demonstrate this. Children, we have an egg here and a sponge. Suppose if we drop this egg on the sponge, what happens is this sponge being soft will increase the time of impact. So, if the time of impact is increased, then the force of impact will be reduced. So, the egg will not break. Let us see. So, when we are dropping from this height, it did not break. This is because the sponge which is soft increases the time of impact. So, the force of impact will reduce, whereas if I drop it down, you can listen to the sound, anytime the egg may break. Even from a smaller height, if we drop, the egg may break. Now, let us see what is going to happen. We have seen that on a sponge the egg did not break, whereas I will drop from the same height, the egg has broken. So, children, in day to day life we find so many situations where if we want to apply lesser force, we have to increase the time of impact. Let us consider some examples. So, if we can increase the time of impact, we can reduce the force of impact. Here are sport shoes. So, whenever we are running wearing sport shoes, the cushion in the sport shoe will increase the time of impact whenever we are running, and thereby reduces the force of impact, and hence we feel comfortable. Here are pads which are worn in cricket. What happens is, whenever a ball which is coming to the batsman, if it hits the pad increases the time of impact and thereby reduces the force of impact, and hence the batsman would be safe. Suspensions in vehicles. Look at this video, children. Here the vehicles are equipped with springs and shock absorbers, which increase the time of impact and decrease the force of impact. Children, not only the vehicles, in most of the situations, for example, in sports, let us say a cricketer who is going to receive a catch. The moment the player stops the ball, immediately the force of impact on his palm will be more. When the player takes the ball, he has to pull it back immediately, so that he can increase the time of impact, and therefore, the force of impact on his palms will be greatly reduced. All the vehicles will be equipped with shock absorbers. Let us see in this video how the ride or the drive will be comfortable with these shock absorbers. So far we have discussed impulse. Now, let us see what happens in a collision. To understand what happens in a collision, I would like to introduce Newton's cradle. This is a Newton's cradle. Here are some bobs which are made of steel, which will be heavy. If you displace one ball and release it, that hits, and the last bob will be displaced. Children, I would like to demonstrate an activity which resembles Newton's cradle. Children, here is a setup. We have two pipes to guide the marbles, and I have used marbles here. Now, let us see what happens. I displace one marble, and then this is going to collide with the first, and the last marble comes out. Let us see once again. if one marble comes out, if one marble collides, then only one marble comes out. Children, here we have set of marbles which are guided by these two pipes. I displace one marble and I push it towards the group of marbles. Let us see what is going to happen. Only the last one has come out. Yeah. Once again. Right. Children, now this time we would repeat the same activity, but we increase the number of marbles. So, we displace 2 marbles at a time and then see what is going to happen. Here we are pushing 2 marbles. So, 2 marbles should come out. Once again, when we push 2 marbles, 2 marbles will come out. Now, we will try with 3 marbles. Let us see, 3 marbles are going to come out. I am going to push 3 marbles, 3 marbles are going to come out. Once again, again. Now, let us see what will happen if we push 4 marbles. So, 4 marbles are going to come out. Let us try with 4. Let us try with 5. If 5 marbles hit, count 1, 2, 3, 4, 5, there are only 4 marbles here, 5 marbles here, 5 will go and collide with these 4. Let us see how many marbles are going to come out. 5 have come out. Children, any object which is moving possesses momentum and kinetic energy, but it is only momentum that will be conserved. Watch it. When this object is moving, it is going to collide with these objects. Yeah. Once again, once again, once again. Yeah. So, in any collision, momentum is conserved. This comes out from Newton's third law, which says every action has equal and opposite reaction. We often see this principle in so many situations in day to day life. Momentum and kinetic energy are transferred in a collision, but only momentum is conserved. So, whenever 2 objects collide, what happens is one object which is moving with a greater velocity collides with another object, and then it applies an action, that is, it applies a force which we call action, and this action has equal and opposite reaction from the other object, and both will be equal. In this example, object B is applying force on A, and at the same time object A applies force on B, and both will be equal and opposite in direction. Children, let us study conservation of linear momentum. Here are 2 objects, mass m1 and mass m2. The object m1 is travelling with the velocity u1 and the object m2 is travelling with the velocity u2. Here u1 is greater than u2. In this case, what happens is m1 is going to collide with m2 and then it applies a force F1 on m2. From Newton's third law, every action must have equal and opposite reaction. So, m2 applies equal force, we call it as reaction, which is F2, and both F1 and F2 will be equal in magnitude, but opposite in direction. Hence, we write F1 is equal to minus F2. After the collision, they move with different velocities. Let us say mass m1 moves with velocity v1 and mass m2 moves with velocity v2. The momentum before collision for marble 1 and marble 2 are m1 u1 for the first object and m2 u2 for the second marble. After the collision, the momentum will change. The momentum of the first marble will be m1 v1 and momentum of the second marble will be m2 v2. The change in momentum for both the marbles is given by the first marble. Change in momentum for first marble is m1 v1 minus m1 u1. For the second marble, change in momentum is m2 v2 minus m2 u2. The rate of change in momentum is given by m1 v1 minus m1 u1 by time t for the first marble and m2 v2 minus m2 u2 by t for the second marble. And these momentums have changed because of the action and reaction forces, which are F1 and F2. Because F1 is equal to minus F2, we can equate them. So, m1 v1 minus m1 u1 by t should be equal to minus of m2 v2 minus m2 u2 by t. Solving this, we get m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. So, conservation of linear momentum says the total momentum before collision is equal to total momentum after the collision. Here the condition is external force should be 0, that is, there should not be any external force acting on these two particles. So, m1 u1 plus m2 u2 should be equal to m1 v1 plus m2 v2. Children, let us revise. Newton's first law, which says every object continues to remain in the state of rest or uniform motion until an external unbalanced force acts on it. Newton's second law, which says the rate of change in momentum of an object is directly proportional to the external unbalanced force acting on it, and it is in the direction of the force. Newton's third law says every action has equal and opposite reaction. We have discussed normal reaction, which will be equal to the weight of the object on a horizontal surface. We have seen free body diagrams. We have seen how to represent a free body diagram when many forces are acting on the object. We have discussed internal force, and we have seen that the sum of all internal forces is 0. We have discussed the equation F equal to ma. Whenever force is acting on an object of mass m, there will be an acceleration which can be found out from the equation F equal to ma, or acceleration is equal to force by mass. We have discussed impulse, which is change in momentum, which is equal to force into time, and we have seen that the force of impact is inversely proportional to time of impact. If we can increase the time of impact, we can reduce the force of impact. We have discussed conservation of linear momentum, which is m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Children, we have come to the conclusion of the unit laws of motion. We have understood the laws which govern the motion of the objects. What I want you to do is observe the motion of various objects which you encounter and try to reason and explain and describe the motion of those objects. We will meet in another class with more interesting concepts of physics. Thank you.